In the last couple of classes, we discussed about amplification in a semiconductor and also the absorption spectrum. We discussed these issues with respect to bulk semiconductors, and today we will see the absorption spectrum and gain spectrum in a quantum well structure. So, recall that we have an expression for gain coefficient gamma is equal to C by n square divided by 8 pi mu square 1 divided by tau r into rho of nu into f g of nu. This is the Fermi inversion factor, which is essentially f e minus f e of nu minus f a of nu, probability of emission minus probability of absorption, which is also equal to f of E2 f c of, if it is in quasi equilibrium, then it is f c of E2 minus f c f v of E1. This is the optical joint density of states rho nu. So, joint density of states. This is the radiative recombination lifetime, and this C by nu can also be written as lambda, but then you have to remember that that is wavelength in the medium, lambda in the medium. C by n by nu is nothing but wavelength lambda, so lambda square. So, I prefer to write it in this fashion. So, this is the gain coefficient. This is gamma greater than 0 if f g of nu is greater than 0, and then we have gain implies gain, and gamma less than 0 if f g of nu is less than 0, and we have attenuation or loss. It is the joint density of states which determine the gain profile. Gamma of nu is primarily determined by rho of nu. So, today we will see the gain and loss in a quantum well structure. So, recall that in a quantum well structure, so let me draw the quantum well structure here. I will draw 3 figures, so you will need space here. This is I would like you to draw 3 parallel figures. So, this is energy axis E versus X. This is EC of the low band gap material, and this is EV. So, this is EG1. So, this is EG of the low band gap material, and corresponding to this, I would like to draw the corresponding EK diagram and the density of states that we have already discussed, but let me draw this. So, the EK diagram, if I plot the EK diagram, this is E versus K. Then you know that at E is equal to EC, we do not have any density of any states there, and therefore, in a quantum well, if this quantum well supports energy E1 here, and so EQ1, EQ equal to 1, so EQ1, let me call this as EQ1 and EQ2. Similarly, for the holes, we have states here EQ dash 1 and EQ dash 2. EQ dash, the dash is just to say that it is basically Q equal to 1 and Q equal to 2. The dash that I have written is to distinguish between. So, let me write E dash Q1 and E dash Q2. That is for the holes. 2 states here and 2 states here. I have taken a quantum well which supports 2 states. So, the corresponding EK diagram, if you plot, we have energy subbands and the subbands look like this. They have the same k square kind of dependence, but only the transverse k, kt, and there is no allowed state at EC, the earlier EC. So, this was EC and this was EV. Similarly, for the valence band, we have, if MC is not equal to MV, the shape would be slightly different. So, these are the energy subbands. This is k axis. For different, what it tells is, for a given value of k, the allowed value of E gives you the EK diagram. So, this is the quantum well. We have also got the density of states. If I had taken the bulk material, this material which was bulk, then I would have had EK diagram going like this. Please remember, right from EC. So, this is for the bulk. The dotted line is showing for the bulk. So, let me write here bulk, and these are for the energy subbands for the quantum well structure. We also want to plot E versus the density of states. So, rho C comma V of E. Just recalling what we have already studied, the density of states. The density of states in the case of bulk had a dependence which is e to the power half dependence. This is for the bulk, and in the case of quantum well, it started, the density of states will start at EQ1, this value here. So, this is EQ1, actually EC plus EQ1. Please remember that the total energy here is EQ1 plus EC. Please add this EC here, because the way we have defined EQ1, so let me write here, EQ1 was h cross square kt square here, h cross square k square kz square, h cross square k square divided by 2 mc. So, this is kz square, which means it is only above EC. Therefore, if I am considering the total energy here, it is EC plus EQ1, this is EC plus EQ2. So, this kz, just reminding you that this kz was q times pi by Lz, q times pi by Lz. If you put q equal to 1, it is kq1 we said, and the corresponding energy we called as EQ1, just to remind you that this was kz in this expression. So, the density of states, we have also derived the density of states. Up to this there is no density of states, but at EQ1 there is a constant density of states here, and then again we do not have any states, constant density of, there is a sudden jump from here to here. This is energy axis. So, this value is EC, this is EC, this is EC plus EQ1. Exactly like that here also, at EV we do not have any density of states, but we have density of states at this value here. You see, this value here is the density of states. This axis is now density of states. So, density of states is constant, this is constant for all energy values here. Up to EC plus EQ1 we have no density of states, which means there are no states. At EC plus EQ1 we have suddenly density of states here, and that density of states is remaining constant, because this is the axis density of states for all energies up to EC plus EQ2. So, that is this value EC plus EQ2, and then suddenly there is a jump which is double. If you recall that this number here was mc divided by pi h cross square into Lz. mc divided by pi h cross square into Lz. Lz is the dimension of this. So, this dimension I had taken as Lz in the z direction, width in the z direction. And this will be double of that, 2 times mc. So, if I write, if you rho c was equal to mc divided by pi h cross square Lz up to Ec plus Eq1, beyond Ec plus Eq1 up to Ec plus Eq2, up to this it is constant, and from here it suddenly jumps to, so this is for Ec plus Eq1 less than E less than Ec plus Eq2, Ec plus Eq2. I have come to the end of the board, Ec plus Eq2, and this is equal to 0 up to this value, equal to 0 for between Ec and Ec less than Ec for all energy values Ec plus Eq, which was not the case earlier in a bulk. And this is equal to 2 times, it doubles 2 times mc. You recall the discussions that we had with the 2 disks when we get a second disk, and this for Ec plus Eq2 onwards, for E greater than Ec plus E. Okay, let me write that, otherwise. So, Ec plus Eq2 less than E less than Ec plus Eq3, and so on. And similarly, rho v will be mc is replaced by mv, that is all. So, the point is you have a step function, density of states is a step function. Same thing is true here, density of states is a step function. So, from here you have the next step. So, photons, this is Eg. In this diagram also you can see that this is Eg. In the case of quantum well, photons of energy equal Eg, energy h nu equal to Eg does not have any state to interact. The lowest energy photon would correspond to this difference, which I call as EgQ1. EgQ1 is Ec plus Eq1 plus E dash Q1. This is the first photon which can interact, which means Eg_Q1 is equal to Eg plus Eq1, this is in the conduction band, plus E dash Q1 in the valence band. So, interaction can take place for photons of energy h nu greater than or equal to Eg_Q1. This is the first point to remember. You can find out the corresponding optical joint density of states. Keep this picture in mind. Let me erase this. The optical joint density of states can be found out exactly like what we had done earlier. If you recall that we had written rho nu d nu equal to rho c of E2 into dE2, therefore, rho nu is equal to dE2 by d nu. E2, we had an expression for E2. E2 in terms of nu was Ec plus Mr by Mc into h nu minus Eg. This is for bulk. Now, E2 is an energy level in the conduction band, which is Ec plus Eg1, and then this difference. So, this will be equal to, though this is for bulk. If you work out exactly similarly, you will get this equal to Eq1 plus Mr by Mc into h nu minus Eg Q1, Eg Q1. Let me erase a little bit here. This is for quantum well. Therefore, dE2 by d nu will be, of course, these are constants, will be as before mr by mc into h. dE2 by d nu is mr by mc into h. All others are constants. mr by mc into h. Therefore, you substitute here rho c of E2. So, this is rho c, I am sorry, rho c of E here, because I am finding rho of nu. Rho c of E was this expression. So, you substitute for the first one. So, this is mc by pi h cross square into Lz into dE2 by d nu, which is into mr by mc into h. That is all. So, rho nu is again constant, just like here it was constant, it is again constant. Rho nu is equal to mc, mc goes here. So, you have mr, 1 h would go here by 2 pi, 2 will come up. So, 2 divided by pi, no, let me keep pi h cross. So, 1 h cross let me keep here, 1 h goes with this, the 2 pi is up, so 2 is there, so pi is there. So, this is h cross into Lz. That is all, which is a constant, which is independent of nu. So, for h nu Eg Q1 less than h nu less than Eg Q2. What is Eg Q1? Eg Q1 is this difference, Eg Q1, band gap from Q equal to 1 here to Q equal to 1. Eg Q2 is this difference. So, the density of states are constant here, and you get the same thing, density of states is constant. So, if I plot this density of states, that is optical joint density of states, how would it look like? The optical joint density of states in a quantum well. So, I plot rho of nu for a quantum well structure. Eg is here, Eg Q1, Eg Q1, Eg Q2. So, this is h nu and rho of nu. For the bulk, x to the power of half dependence. So, we have a constant here, so the density of states is constant up to Eg Q2 and then jumps up again, remains constant up to Eg Q3. The value here, this value here is 2 mr into h cross Lz. So, this value here is 2 mr h cross Lz. And what would this be? 2 times 2 mr h cross Lz, double. The density of state simply doubles. So, the optical joint density of states in the case of bulk was varying like this. In the case of a quantum well, it varies like a step function. This is important because we want to get the gain coefficient and loss coefficient, because the profile, the gain profile and the absorption spectrum is determined by rho of nu. This is just the derivation, which is just an extension of the derivation of for density of states. So, let us now find the gain profile, okay, gain spectrum. So, let me draw it here. Let me draw afresh. I want to draw in the same line 3 curves, one below another now. So, first one is density of states. So, the bulk is here. So, this is rho of nu versus h nu, the variation for a quantum well structure. This is Eg, this is Eg Q1, Eg Q2, I want to plot also Fg of nu. Let us recall the thought experiment that we had done at 0k. At 0k, up to EFC minus EFV greater than 0, up to an energy which is equal to, let us say we are here. This is h nu, this is Eg, and this is EFC minus EFV. Recall what we had done, EFC minus EFV. That is the separation between the Fermi levels. So, I am now looking at this semiconductor which is in quasi equilibrium. This is EB, this is EC, and EFC has entered the band, EFV has entered the band. So, this is Eg and this is EFC minus EFV. So, EFC, EFV. What we had seen was for all h nu between this and this, if I take 0k, experiment at 0k, then Fg of nu was +1, and for all others it is -1. If it exceeds, it is -1, which means if I plot Fg of nu here, Fg of nu, then it is, this is +1, and this is -1. So, it remained +1. This is experiment at 0k up to this, and then it went down to -1. The step function. This is EFC minus EFK, Fg of nu, the probability of emission minus probability of absorption. The Fermi inversion factor was +1 up to this and -1 up to this. And accordingly, if you recall that the gain, if I had the EFC minus, let us say EFC minus EFV was here, EFC minus EFV. So, I could show it right here on the same, over this, or let me, on the same line, let me show this here, because all the 3 figures which I will get one below another. So, this is EFC minus EFV. So, the product of rho nu into Fg of nu. For the bulk, we had a gain profile which went up to this and then it shot down. So, I will draw it here just to remind you how it was there for the bulk. So, the gain profile went like this, it followed exactly rho of nu, and then it came down, because beyond this value we had h nu versus gain, so gamma of nu, and at 0k it did this. So, gain, it was positive, negative beyond EFC minus EF. this was for T equal to 0. At a finite temperature, this changed to this. Why did this change? Because Fg of nu was no more a step function. Fg of nu was varying like this. That is why this changed over to this. So, this is for T equal to 0 K, and this is for T greater than 0 K at a finite temperature. That is for the bulk. I want to draw the same thing for quantum well structure. So, if I want to plot the same thing for quantum well structure, let me plot it here below. So, this is rho of nu. I want to plot gamma of nu. The third figure. So, how do we go about this? First, let me plot for 0 K. So, it is plus 1 or minus 1. So, the gain will be this into this. The density of state starts only here, from here. Therefore, the gain will also start from there, and the gain will remain constant like this, same as this multiplied by this multiplied by this, two functions. So, first function rho of nu is varying like this, and Fg of nu is also varying like this. So, I have let me draw this fully. Why draw? Because there are so many dashed lines that you might have confusion. So, let me draw it fully. So, that is Fg of nu. So, the product of these two is constant. When you come at this value Eg Q2, there is a jump. So, the gain would also just becomes double, because the density of states become double. At this value here, so this has gone up to this, but the next Eg Q3 has not come, but at this value we have Fg of nu becoming negative, minus 1. This is minus 1 here, and therefore minus into this. So, we have the gain dropping down like this, and this will become like this. So, we have gain profile which is a step function at 0 K. So, what I have plotted is the gain profile. Please remember, at Eg there is no gain. This value is Eg Q1 and this value is Eg Q2. So, what is the point? Wavelengths or frequencies which correspond to within this band from here to here, the gain is constant, flat, it is a flat gain. Similarly, for frequencies from here to here, gain is flat, but a different value. It is a step function. This is at 0 K. If I go for a finite temperature, Fg of nu will get modified. So, this will get modified and this will cross here and go in this fashion. So, this is Fg of nu for T greater than 0, greater than 0 K. The step function was for 0 K. So, this was for T equal to 0 K. Fg of nu does this just as before. Therefore, the gain here would also, it is a product of these two, this remains constant, but this is a product, and therefore, if you multiply, initially it will remain the same, but slowly the difference will start coming up. So, it is separating out, it is coming down here, there is a step here no doubt, but it is separating out, and then when this becomes 0, the product is 0. So, this will pass through like this till the next step. There will be a next step here and you will have a step here and then the second step which is coming, but that is the absorption part. Gamma is positive, gamma is 0, gamma is gain, and this is loss. This loss part we will discuss separately. So now you see that in a practical amplifier, quantum well amplifier, the gain will have a spectrum like this. You can see in the literature, let me just open it up a little bit. You can see actual calculated and measured gain profiles in the literature, and you will see them. Indeed, there are step-like variations. So let me just widen this range and show you how in practice the gain of a quantum well amplifier looks like. So typically it looks like so what I have plotted is gain coefficient versus energy. So this is the value where gain starts at EgQ1. Please remember EgQ1, not Eg. And this is the jump here is at EgQ2. And obviously this crossover point is always EFC minus EFP, which determines the amplification bandwidth. The amplification bandwidth in this case is always EFC to EgQ1. In the case of a bulk amplifier, it would be EFC to Eg. Eg to EFC is the amplification bandwidth. I am not calling it as a gain bandwidth, because gain bandwidth is normally defined as the frequencies at which the gain falls to 3 dB, that is falls to half. So this I am calling as amplification bandwidth, because in this for all frequencies in this range you have gain. So we call it as amplification bandwidth. In the last class when we had written the expression, it was for amplification bandwidth. So in this case amplification bandwidth is determined by EFC minus EFV minus EgQ1 divided by H. So this is the amplification bandwidth delta nu. H delta nu is the energy difference, therefore H delta nu the bandwidth is given by this for a quantum well structure. If you design properly, it is possible to get this crossover right here EgQ2, because I need to pump only that much, so that the separation between EFC minus EFV is here, and you will have a nice amplifier like this, almost flat. It is almost like a box type. It is an ideal amplifier characteristic is you want the gain to be flat like a box. So if you properly design and shift this here, of course the range is small, but you will have a box. So this is gain versus frequency or energy, a flat band amplifier, quantum well amplifier. We will discuss more about these quantum wells at a later stage. Let me now come to attenuation spectrum, loss spectrum. Identical discussion, but you see only difference when we discuss about attenuation and gain is, remember that the gain bandwidth, amplification bandwidth is very small in the frequency range, about 10 to the power of 13 hertz. Whereas when we discuss about loss, we are discussing over a very wide spectrum. We discuss the gain spectrum over a loss spectrum over wide energy range, because if you take silicon detector for example, it can detect anywhere from 0.4 micrometer, that is visible, down to 1.1 micrometer. So it is a large energy h nu range. Whereas the gain bandwidth is much smaller compared to the absorption range. And and therefore what is the difference? We have to also include the effect of this nu. In discussion of the gain, we take this as constant because the range is very narrow, therefore we say that okay, over the range of interest 1 by nu square variation is neglected. But in the case of loss spectrum, we would like to keep the 1 by nu square dependence. So let us, because I am still keeping the same expression here. If Fg of nu is negative, let us take for example room temperature, a normal semiconductor at thermal equilibrium. How would it have the, so this is EV, this is EC, and the EF is somewhere wherever you want, a normal, so EF is somewhere here, which means if you plot the Fermi distribution, so what I have plotted on this axis is also f of E, thermal equilibrium, normal semiconductors, absorption spectrum I want to determine. So this is EF and this is f of E, which is 1.0 here and 0 here, and how do we determine the Fermi energy? Here it is 0.5. Okay, and therefore Fg of nu here, Fg of nu or Fg of E, so is equal to f of E2 minus f of E1, f of Fg here equal to f of E2 minus f of E2 is any energy value here. So this is E2 and E1 is some value here in the valence band. So this is the valence band, this is the conduction band. F of E2 is a very small value here. If you put actual numbers, as I already mentioned, it will be very 0.0001 or something like that. So very small value, and f of E1 is very close to 1, 0.9999, which means this is 0 minus 0.99, so it is approximately equal to minus 1, approximately a little less than minus 1, but approximately equal to minus 1. So I can safely write alpha minus gamma equal to alpha A equal to is approximately equal to C by n whole square 8 pi into tau r into rho of nu divided by nu square. Fg of nu I have written as minus 1. So minus sign was there, and that is the attenuation coefficient. For a quantum well structure, rho nu is a constant, it is a step function up to certain energy. So what kind of attenuation spectrum would you observe? So let me plot the attenuation spectrum. What is expected? So this is h nu, 1 over nu square is a monotonically dropping function. 1 over x square dependence. Remember that we are coming from a long range. So this is continuously, this is actually going like this and going down to 0. So in our optical region, this is continuously dropping like this, 1 over nu square. What is rho nu doing? Rho nu is a step function. So rho nu is constant, it is a staircase like function. So this is rho of nu. Where does it start? This is EGQ1, EG is somewhere here, EG, and this is EGQ2. Remember again, what is EGQ1 is the difference between the first subband in the conduction band to the first subband in the valence band, and EGQ2 is the difference in the second to the second. So this is EGQ2, and so on. So the product, this is a very small variation, but nevertheless if I multiply this and this, what you expect is a function which is the product expected. So, this is the upper one is rho of nu and the lower one is alpha of nu into some constants are there, but the variation I am showing only the variation. So, this is alpha of nu. The important point you see in a quantum well structure is a step like variation. So, if I now forget all these expressions and compare the attenuation spectrum of bulk and quantum well structures, what do we expect and where is the difference? A bulk semiconductor, let me take a direct band gap semiconductor like gallium arsenide. So, this is h nu and this is Eg 1.42 eV, 1.42, that is Eg, EV, and let me draw some values, I do not know, let me spread 1.42, this is let me say 1.6, 1.8, 2.0, 2.2 and so on, EV, h nu in EV. And this is alpha axis, alpha centimeter inverse, and typical numbers 10.2, 10 to the power of 2, 10 to the power of 4, 10 to the power of 5 and so on, centimeter inverse. In the bulk case, we would get a dependence which would be something like this. Compared to what I had drawn earlier, I have tilted this. You remember earlier when I had drawn almost short vertically and then, but remember my scale was different. It was going to 3, 1, 2, 3 EVs. Now I have just expanded the scale, that is why it is slightly tilting, it is slightly going at an angle because of the expansion in the scale. I had to expand because these differences are not 1, 2, 3, it is a small difference because it is corresponding to the energy difference here in the quantum well. It is only 50 to 100 MeV difference, it is not difference, that means 0.1 EV is the difference between these two, not 1 EV. That is why I had to expand this to be realistic. EgQ1 will be somewhere here and EgQ2 may be somewhere here, 1.58, approximately 1.4652, something like that, approximately. I am just giving you an idea, but how do we expect? We expect that this should go up like a step function now, not like in quantum, it is almost a step function and then it becomes flat here and then again a step function a little bit downward. And you indeed see this when you measure. I will show you the measured spectrum, how does that look like. So you see, you expect a step like variation. A measured spectrum almost shows this. A measured spectrum, if I plot on the same, so let me just for differentiation, let me make this, this is theoretically what you expect. If you expect this theoretically for a quantum well, this is for the bulk gallium arsenide, starts from Eg. First difference you see is this starts at EgQ1 and then it is a step function. So, this is for a step function, quantum well. What is measured shows a spectrum a little bit earlier, it starts, it goes like this and then it shows a little bit of peaking like this, and then of course it continues there, again it comes up, a little bit of peaking, and then it goes like this. So, on the same thing there is a little bit of peaking which we see in a quantum well, absorption spectrum of a quantum well. So, this is the measured one. So, this is measured. This is theoretically expected and measured. So, one thing is sure, it shows a step like variation, but there are some peaks there. What do we think is the explanation for these peaks? These peaks correspond to excitonic peaks. So, the peaks correspond to excitonic resonances. These play a very important role in the device that we will discuss, quantum well modulators or electro absorption modulators. The peaks correspond to excitonic resonances. In the bulk case, we do not see anything. All these measurements are at room temperature. So, this is at 300 K. We are able to see excitonic resonances in the case of quantum well structures. Why do not we see that in the case of bulk? Let me stop here this discussion and continue in the next class because we have to take a quiz now. There is a very interesting explanations and discussions follow, but I will continue in the next class. So, please let us take a quiz. A simple quiz. All quizzes are very simple. Let me read it for you. A particular semiconductor laser amplifier with indium gallium arsenide phosphide active medium of Eg equal to 1.24 eV has a peak gain coefficient of 75 centimeter inverse, peak gain coefficient, that is peak of the gain spectrum, and amplification bandwidth of 100 nanometer. It is in wavelength now. 100 nanometer is the amplification bandwidth. Making use of the above data, draw qualitatively the variation of gain spectrum with wavelength in the amplification band. Variation of gain spectrum with wavelength in the amplification band. We have drawn this many times with the energy. So, you have been asked, because in practice normally we discuss in terms of wavelengths in optics. So, plot the variation of gain coefficient qualitatively with wavelength, gamma of lambda versus lambda, qualitatively gain variation with wavelength. Should not take more than 2 to 3 minutes. If you have completed, you can leave.